Hi there, Matthew Gosdale here again with another lecture on PCG. This is again for the Game AI course out of the University of Alberta. Today we're going to be focused on search-based procedural content generation, or SBPCG, because if there's one thing academics love, it's acronyms. So as a reminder, if you're actually in this class and you'd like to get credit for actually watching this lecture and filling out the questions for it, please go ahead and follow either of these two links. They'll take you to the same place. You can also just go to tinyurl.com/GuzSBPCG. Okay, probably get enough time for that. Let's move on. So quick review from the content we talked about last time on Monday. We basically introduced two kinds of PCG. The first is constructive PCG, which is basically various approaches for putting together existing content piece by piece. And then we had search-based PCG, where the idea was to search across complete pieces of content for the best according to some fitness function. So we're not actually going to construct things piece by piece. We're actually just going to search across whole pieces of content and see what we can find. So there's some vocabulary that search-based PCG uses that I wanted to introduce up here at the top, as I'll be using it throughout this lecture. First of all, we have the notion of a search space. So a search space is a space with generally fixed dimensions where every point of that space is an entity. We'll just use a lowercase e for that, which is a complete piece of content. This could be a song, a story, a video game level, a character, a flower, whatever you can imagine, right? Anything that you're trying to generate that's an entity, and every point of this space is a complete one of these entities. Now, that says nothing about their quality, right? Their quality, we're going to evaluate with something we call a fitness function. This actually goes by a lot of names. Some people will just call this a heuristic. Some people will call this an evaluation function. Regardless, it's a function that's going to map each entity to some numeric value that tells us the quality of that entity. How good is it for one of whatever it is? And then we have a neighbors, which I'm going to do is represent as big N of E, where it's the entities or next things to this particular entity. So we can sort of visualize the space as looking a bit like this, right? Where we have all the entities, let's pretend we could put them all on one line, right? And then we have this y-axis here being the fitness. So these little units up here would be the most fit, then less fit, and 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 then less fit, and then less fit all the way at the end. And then we have a little bit bump over here where maybe this one little spot is better than the places next to it, according to whatever the fitness function this is. I don't know what fitness function this is. Just imagine something, right? Maybe it's the number of enemies in a level, or it's the symmetry of a flower, right? This could be anything. Specifically, let's look at an actual example of what it might be. So, for example, let's think about weapon generation. So in weapon generation, right, we might imagine we have two variables that we actually care about when it comes to generating a new weapon. And those two variables that we care about, damage, the minimum damage being here, the maximum damage being up here, and then speed, the minimum speed going over here, the maximum speed going over here, would define a space, right? These two variables define a space. Now, in all probability, if we're generating weapons, we probably have way more spaces than this. But I unfortunately can't generate a 3D image to mess around here, and certainly not a 4D or 5D image, though I wish I could. Though, of course, those things we're generating have more than just two variables, which means they have more than two dimensions. But we're going to have to stay, unfortunately, in the one dimension, the two-dimensional space for now. So if we have this, we can imagine then the color here representing the fitness. So the white or the lighter blue, the better, basically. So we have this dark blue band here, which is saying these are the worst possible weapons you could make. So let's say I end up right here, right? This would be a low speed and a low damage weapon. Up here would be a high damage, but a low speed weapon. So our fitness function is saying that's good. That would be a good kind of weapon to make. And then over here, we could have a high speed but a low damage weapon. Again, our fitness function is saying this would be a good thing. And up here at the top, we would have a high speed, high damage weapon, which our fitness function is saying, no, that's a bad thing. All right? So the idea would be that maybe we'd start, say, right here, and then we'd look around the space trying to find the better and the better and the better thing until we finally ended up here. And maybe we ended up over here actually initially, and then we'd look over here, over here, over here, over here, until we ended up in this space. So what I've just described is the simplest method for doing search, really, but search-based PCG as well, and that's a greedy or hill climbing search. So let's go through some pseudocode. I'll explain what every line is doing if you're not familiar. So to start with, we're going to pick our current entity by picking some random starting position. For example, way back over here, right, we could pick somewhere through here. Literally, we could start anywhere. Then we're going to start a while loop. And while our fitness is less than some threshold, we're going to iterate. In every iteration, we're going to grab the neighbors. So what are the next locations to this current entity? What are the places we can get to from where we are? Now, notably, each place is also a thing, right? So each of these neighbors are themselves an entity. So if this is a weapon, these are also weapons. The only difference is that those variables that they're defined by are slightly different. So then we're going to iterate through our neighbors. And then if the fitness of this neighbor is better than our current entity's fitness, then we set our current entity to this neighbor, right? So our neighbor becomes the current entity. And then we just keep going until we hit this threshold, and then we return the current entity. Now, you might want to have a break over here. Say we can't actually hit this threshold. Let's say that our fitness function goes from 0 to 1. Our threshold is 0.9. But the best possible thing in our space is actually at 0.8. So maybe in that case, we want to have some secondary condition on this while loop saying, once we've checked 1,000 times, or whether we've been caught on this current entity for a long time, right? We can't do better than this current entity, then go ahead and just return that. So this is the simplest method, which means that it's going to have some issues, right? So the first issue is, what if this search space looks spiky, right? Well, if we randomly choose our initial starting point is here, no problem. We can follow this point, all these neighbors, all the way up to here to the very best thing in this entire search space. But what if our initial random starting place is right here? Well, then according to that, we can't go this way because that would be worse. We'd be going lower with our fitness function. We have to go up here, up higher. Now, as a reminder, if this is hard to visualize or hard to think about, now this search program, the search algorithm, they don't know what this whole space looks like. If we knew what the whole space looks like, if we could see this whole space at the same time already, then we could just, pick the best thing. But that would require doing an exhaustive search of the whole search space. And that might be really big, right? This might be a continuous variables, at which point it could go on forever. So instead, all we know is the place that we're at and the places that are next to us. Which is why, then, the greedy search always just goes for the next best thing, right? And if there's nothing better, then it gets stuck. So if we started here, we'd go up this hill until we get stuck right here. And we call these little small hills local maxima. It means basically that there's a point in the space where all the neighbors of that point are worse than it. So then the best thing in the space is called a global maximum. Now, there might be multiple best things, so things that are tied for this best position. Say if this one also had a spike that went up here, then there would be global maxima. So that's one issue. Another issue, what if this search space looks like this? Well, it's fine if we randomly choose up here, but if we choose a spot down here, we're going to end up searching for a really, 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 really long time, right? We would end up searching for the majority of our search space's size. That could be massive, right? If this is continuous, let's say this is like, I don't know, 1 billion points, all right? Then we would at least have to get very, very close to a billion checks just to be able to get up here. That's a lot. So that's not ideal either. So greedy search has some pros and cons. The pros, it's simple, right? I can explain it in 5 lines of pseudocode. I could write it almost as simply. In fact, I'll show you that in just a second. And it also, depending on the space, can get a result very quickly. So if all we care about is getting a result that's pretty good, and our space sort of fits that, we're fine, right? If we can just return a local maxima, get our local maxima real quick, no problem. So there's cons, of course. Depending on the space, it will be unable to find a global maxima. Not necessarily unable, right? If we just kept running it over and over again for infinity, maybe eventually we could figure it out just because we're randomly having a random starting space. But we wouldn't want to do that either. And then if you're in a space simple enough for greedy search, why are you even doing search? Why not just do a constructive PCG? So these are the kinds of issues that you'd have just trying to run greedy search to do PCG. But that brings us to our first question. So for those of you in the class, name a kind of entity. This could be a level, an enemy, a song, a decoration, etc. What could the neighbors and the fitness functions look like? So what would it mean to turn one level into another level, or one enemy into another enemy? That's what the neighbors function would give us. And then fitness functions, what does it mean for a level to be good, or an enemy to be good, or a song to be good? This can be as specific as you like to a particular domain, to a particular instantiation of a level, whatever you like. I just need something here, some thoughts put into here. If you're not in the class, just think about this for a couple minutes. All right, let's go. Okay, that seems like enough time. Right, so instead of just giving you an answer, let me give you a longer example. So I've made another little Unity project. This one's to show off search-based PCG. So you'll note right now that we have a sample scene, we have a main camera, and we have a giant background. Because what we're going to be doing is generating platformer levels. So I've constructed a few prefabs ahead of time. It feels a bit like a cooking show to have done this. But I've constructed a few prefabs ahead of time that will represent sort of pieces of our platformer level. So let's see here. So we have a 4 tall columns, a 4 tall columns plus fence, a 4 tall columns plus a little fly, 4 tall columns plus an item box, 4 tall columns plus a platform, 4 tall columns plus a sign, plus a snail, nice little snail, a 6 tall column platform, also with a fence, basically with all the same variations, and then we have a gap that has a little bit of water, and then a gap with a platform on it. And each of these has a very simple script called column info that just basically is going to store some information about this specific column. So we have the height, we have whether or not it has an enemy, the enemy type, it's 1 for a normal enemy and 2 for a flying enemy, whether it has an item, whether it has decoration, whether it has a platform, and what the height of that platform is. So I'm going to go ahead and delete this. Let's just run the code and see what we get. Okay, so here's our level. Now, this looks maybe okay, depending on what you think. It's a little busy. Now this is, I will note, the Kenny platformer art set. I'll have a link to it in the description. This is a little bit messy. Let's take a look at what the code is doing that's making this level. So if we open up main camera, we can see that on that, besides a camera mover script, we have a level generator.cs script. So let's go ahead and take a look at that, if it will open for us. There we go. Okay, so what are we doing? First of all, we have a list of our columns, all of those columns that I just showed you. We have a particular width of our column. We have a level length that we want to have, how many columns we want to have in our level. We have a starting position, where do we want our level to start. Then we have a threshold and max attempts, neither of which are being used right now. So all that's happening right now is that we're creating a random level. We're figuring out the fitness of that level, not doing anything with that, and then just going ahead and visualizing the level. So this random level, all it does is iterate through our level length, so 100 columns, and just randomly assigns a random column to each position. So right now, this is just constructive PCG, right? But let's make it search-based PCG. Simple enough to do that. I just need to uncomment this code. Now, unfortunately, all code doesn't come with an easy search-based PCG thing for you just to uncomment, but let's go ahead and talk about what the difference is here. So this is basically just a hill climbing greedy search. So we have a steps thing here we're tracking to make sure that we don't just run forever. We have a while loop here where our fitness of our current level is under some threshold, in this case 0.95. We have steps, so steps plus equals 1. This is just to make sure we don't go on forever. We have a get neighbors level function. Now this is sort of the core, the crux of this thing. What we're going to do for our get neighbors function is we're going to iterate through every position of our current level, and where that position could be different, where it could have some different value, we're going to clone our level and change that to that new values, that new column, swap a column out, and then just add that to our list of neighbors. So basically we're making every possible change, every possible, well, single change. That's what neighbors are. It's every possible change we can make to this current level. Let's go back up here. So then we're going to check and see what the fitness of this thing is. Let's actually take a look at that function. So right now, we just start with our score equal to 0. Oh, I should change this to a float. There we go. Then we iterate through every position in our level. And if our height of our column is 4, then we're going to increment our score by 1. We're then going to go ahead and divide our score value by the level length to normalize it. So now it's going to have at most a value of 1, and then return the score. So we have at most a value of 1, and we want a threshold of 0.95. So let's see what happens when we run this. So obviously then it's going to iterate. It's going to pick the best neighbors. When it either can't find a better neighbor and the steps go to max steps, or when our fitness is above our threshold, then we're going to stop and we're going to debug, log, print out the fitness, the number of steps we took, and we're going to visualize the level. Let's go ahead and hit play again and see what happens. Okay, so this looks a lot calmer, certainly, but pretty darn boring. What we're basically doing is incentivizing having a very linear level, a very flat, boring level. Even then, if we take a look here, our fitness only got to 0.95. That basically means that 5 of our positions still didn't have a height of 4, and it took us 50 steps to get there, which is quite a while. It took us quite a bit to get there. So let's pause, or hit play again, hit it again, and take a look. And every time we do this, it's rerunning that search. That time it took 53 steps. This time it took 48, and it's going to be a slightly different level. Okay, so that's not all that interesting, right? What can we do to make this better? Well, the easiest thing to do is to change out our fitness function. Right now, we have a fitness function which is encouraging having levels where it's all flat, which is really boring, right? If this is a platformer level, we should definitely at least have, gaps, maybe. So maybe we'd do that instead. Maybe we want to have a fitness function which is encouraging having more gaps. In that case, we would want our height to equal 0. And we can go ahead and run this again. Okay, well, because we wanted a threshold of 95, that means that we're basically saying everything should be flat, except right here at the very end. Well, that's no good, is it? I need to stop hitting that Microsoft PowerPoint application. So let's think for a second. What could we do different? Well, what we could do is we could change this fitness function, right? So instead of giving the best possible score when the whole level was just gaps, instead maybe when half the level is gaps. We could also do something like just return when we have a lower threshold. So we could drop our threshold to like 0.5. We could do something like that, but that isn't really very neat, right? We would still like it to be the case that the best possible level is still, has the highest fitness. And that wouldn't be the case here. We'd be sort of tricking it by forcing it to stop early. But the best level, according to the same fitness function, would still be that all no gaps level. So rather than changing this, let's go ahead and change our fitness. So if we're going to change their fitness, what we really want is some situation where our score is the best when we have a level of half gaps. So let's take a look here. So what we could do is we could say something like our score is going to be equal to score minus, well, we want math, absolute value of the score minus the level length divided by 2. 2f, make sure this is a float. So what this is going to do is it's going to look at what the difference is between the current score value, which as a reminder right now is associated with the number of blocks we have, the number of gaps we have rather. We could actually just change this out to make sure that it seems right. So let's call this the number of gaps. I'll just call it gaps. Increment it by 1. Do this and do this. So this is now going to say that the score is going to be equal to the difference, how far off the number of gaps is from half of the level length. So 50 gaps in this case. How far off are we from 50 gaps? Now at most, this could have a value of 50, and we'd really like it to scale it back to a value of at most 1. And we really want to incentivize the opposite of this, right? Where instead of saying the further are you off from 50 gaps, the better, it should be the opposite, where the closer you are to 50 gaps, the better. So we're going to take this, we're going to do 1 minus this value, and then divide this whole value by the level length, half the level length again. Okay, so let's go ahead. We don't need to do this anymore because we're already normalizing it. Let's go ahead and rerun this and see what we get. Okay, now this is interesting. If we take a closer look, we can see that exactly half the level, in fact, the first half of the level, is all gaps, is all empty, and then the second half of the level is mostly still filled in with stuff. So that's weird, right? But actually, if we think about it for a second, it's not, because of how our neighbor function works. Our neighbor function is going to produce neighbors going from the start of the level to the end of the level, which means that as we're producing neighbors, we're going to get to the best neighbor, where half of the level is all gaps, by going from the left to the right, right? So the first half of the level is going to end up being all gaps. So what we really want to do here is not have an ordering problem in our get neighbors levels function. So that's a pretty easy thing to fix. Thankfully, like all good chefs, I have some code prepared. Basically what we're going to do is we're going to iterate through our list of neighbors, and we're just going to randomly swap indices. So make sure that we don't have that same ordering effect, that problem. So let's go ahead and hit play again and take a look. Okay, now that's looking quite a bit better, right? Maybe it's still not great. We still have like a lot of weird uniformity through here that doesn't look maybe perfect. But that's starting to feel more like an actual platformer level, maybe. I'm going to hit it again, take another look. We can see this one has 0.96 fitness, so almost exactly half. Do it again. maybe we're looking at this and we're thinking, well, half might be a bit too much because we're still getting cases where we have, like here, for example, almost literally just something, gap, something, right? Which we could just have through this whole level, and that would technically be for the best. So maybe half is too much. Maybe what we actually want is something more like, I'm going to close this for now. Maybe we want is something more like, I don't know, a third, right? So when we have a third of the level is all gaps. Let's run that again and take a look. Okay, so we're having bigger patches of ground now with gaps in between. That's looking a little bit better, but we're still having this weird issue. Like especially, we have a lot of enemies in this level, don't we? So maybe we could do something about that. Okay, so let's go back to our fitness function, and now let's try to track enemies as well. So if this particular column has an enemy, let's increment that. Okay, so now we need something where, just as before, don't listen to what they tell you in school, you can copy paste code all you like. Now what we can do is just do some pretty easy changes and say something like, okay, maybe we want a tenth of the level to have enemies. Now to make sure that we're still normalized, that we still have a maximum value of exactly 1, just to make sure we don't have to mess around with any other parts of this code, we can just go ahead and divide the score by 2. And let's go ahead and rerun this. Okay, so immediately now, this was 0.95 in 18 steps, so very quick. Immediately now we can see that we have a lot less enemies. Now the enemies we do have are maybe sort of clustered together. Maybe we could change up our fitness function again to track something like that, how close they are. I'm gonna run this again. Okay, that looks better. You have a nice breather here, then a few more enemies, and then a bit at the end. Now we also have this issue where we have a lot of platforms, huh? Just tons of platforms throughout this thing. And while this is a platformer, we already have gaps. So let's go ahead and add one more part to this fitness function to track platforms. Now notably, this is the kind of thing that search-based methods allow you to do. If this was a constructive method, I would have to go in and write a whole bunch of rules, right? Like we did yesterday, to be able to specify things. And I'd have to specify things based on local information. So based on what this slot has, I make a decision based on the next slot. But with this, I can just tell it, hey, I want this to be true. I want levels that kind of look like this. And as long as I can take what I want and sort of turn it into some impact here on the fitness function, then I can make it a reality. So again, I'm going to say I just want a tenth of the level to have the floating platforms. Let's hit play. Okay, there we go. Now maybe again we want to do something about that decoration, but this is starting to look, quite a bit better. Maybe you liked the earlier version where it was messier earlier, but this is definitely more intentional looking, if nothing else. So we could keep iterating on this for a while, but as we're going to keep going, the fitness function we're going to need to be able to do what we want it to do is going to get more and more complex. I'm going to have to balance more and more things. Say we wanted to check and see if the level was playable. Well, in that case, we need to run an agent, maybe like an A-star agent over the level, just to make sure, hey, this level is playable. And then incorporate that into the fitness function and somehow balance out all these different features. As it is right now, we're balancing out the number of gaps, the number of enemies, and the number of platforms all equally, right? They all have a third of an impact on this final fitness. But maybe that's not right? Maybe instead we want to say, oh, the most important thing is the gaps. Then come the enemies, then the platforms. There's lots of ways to do this, and lots of ways that shaping this fitness function is going to give you control over the kinds of final levels you get, the sort of possibility space of your possible output from your generator. And that's sort of the crux of search-based PCG, the ways that you have impact. Instead of just changing things in terms of the constructive approach of hand authoring new chunks, new pieces, and then rules for putting them together, instead, mostly what you're doing is you're authoring new changes to your fitness function, seeing what that does, and then making more changes from there. Okay, let's try one more thing before we head back to the slides. So far you'll note that we've gotten pretty lucky, and we haven't had just gaps right at the beginning of the level. But there's actually no guarantee right now that we won't have just a gap to start our level with. And if, for example, our player spawns right here, our player would just immediately fall into the water and die, assumably, if gaps killed the player. Now, that's maybe not ideal. So another way that you can impact your fitness function is by having more sort of direct things show up in terms of what's happening in your fitness function. So we could do something like, say, if the columns, let's see here, if the columns, if the value of I, let's say, is less than 3, so we want the first 3 values of our level to not be gaps. If the value of I is less than 3 and this is true, then we're going to go ahead and just return 0. Let's go ahead and see what happens when we try to do that. It's an easy way to think about this, right? We would say no level is good if the first 3, if any of the first 3 of units of it, any of the first 3 columns of it are gaps. Let's go ahead and see what happens if we try to do that. Okay, so we got a fitness of 0 after 100 steps. Just because we happen to get to the case, right, where our first column, this is just luck that this happened, our first column happened to have a gap in it. Let's run it again and see. Okay, so again, this case, our second column happened to have a gap in it, and again, we had a fitness of 0 after 100 steps. So what's happening here? Well, what's happening is our very first random level happens to have a gap in one of those first 3 columns. Now, because of that, we get 0 every single time for every single level variant from there. Which means if everything's 0, we can't possibly get better, right? Because none of our neighbors ever look better because everything is 0. It's a flat space. It's just a line. So that's no good, right? We can't just say, hey, it's 0 if we have that being the case. So instead, maybe what we do is we have some score modifier. And we're going to take our score modifier, and we are going to say that it is going to get a little bit lower, maybe 0.1 lower, every single time this is the case. And then we can just add that to our score. Let's go ahead and rerun this. Okay, so after only 40 steps, we managed to get 99% of our fitness function. That's pretty good, right? Let's run it again. And again. So these are the kinds of things that you have to think about when working with search-based PCG as well. Just the fact that we changed our fitness function in one way meant that we could never, ever get better than an initial random starting point. Okay, let's head back to the slides. Okay, so hopefully that was helpful to give you some intuitions about how you can work with search-based PCG. So let's actually just jump directly into another question. Here's the question. How could we get out of a local maxima? Let's say that we got stuck here. How could we possibly get out of there and make our way over to here? Now, as a reminder, while I'm showing you the entirety of the search space, just for the example, if you are an agent or a search algorithm, you only know about what is local to you. Okay, so take a couple minutes, give this some thought. And if you're watching ahead of time, if you're watching this later, go ahead and just jump forward, and then we'll jump back into it. Okay, so here's one way that we can get out of a local maxima, and it's called a random walk. Basic idea is that instead of taking the next best from all the neighbors, we're going to just take some random neighbor. That's going to let us actually go downhill, right? Instead of having to go up these sort of hills of better fitness, we can go downhill for the first time, or even traverse along flat plateaus. And then at the end, we just pick the best point we ever saw. Now, this isn't perfect, right? Because we can just easily get stuck going back and forth forever, right? We could just go back and forth between the same two neighbors for all time. There's some ways we could get around that, right? We could track where we've been, make sure we're always going somewhere new, make sure we're exploring the space. But even then, we could just get caught going in like big circles or big spiral shapes. So we don't want to just entirely get rid of the idea of hill climbing or going for up the fitness, going for the better things. But we also can't only do that. So can we combine random walk and a greedy search? Well, yeah. The simplest way to do it is called simulated annealing. Simulated annealing used to be pretty big a while ago, but nowadays it's more sort of used in very specialized area. But it's a good example of how we can go about combining a random walk and greedy search or hill climbing search. So what I've done here is I've given you the pseudocode for simulated annealing, but I've bolded all the changes from just the hill climbing or the greedy search. So what we do is, first of all, we're going to instantiate a value named t. This is called a temperature. The idea here from simulated annealing actually comes from smithing. The idea is that we're going to start at a very high temperature, which is going to lead us to occasionally taking more random actions. And then as our temperature cools, according to some rate of decay, then it's going to become more and more likely that we just take better actions, that we just go with the best neighbor possible. But this allows us to sort of explore it first, and then as our temperature decays, to go more and more trying to head towards better and better places to be. Now, there's no guarantees we're going to find our global maxima, but if we're wandering around at first, and then we're picking our next based on how good it is or how much better it is than where we were before, we might climb up this hill, then climb down, but then, oh, hey, this is so much better than it was before. So as our temperature cooled, we're more and more likely to follow our way up here, as long as we can make it to this sort of area during our random walk at some point. And that's fairly likely, but again, there's no guarantees. So has simulated annealing solved all our problems? No, unfortunately not. Here's an example of a situation which would be really bad for simulated annealing. It could get caught on all these really nice local maxima, and because it's so bad around this one really good position, it'd have a really hard time of making its way all the way down here and to be able to start making it up and climbing to this top. Now, maybe you think this is unusual space, but unfortunately it's really not. There's lots of spaces where there's a lot of sort of bad stuff and then some good stuff, which is even not that different from the bad stuff. Think about level design, for example. It's not hard to make a really good level a really bad level by just making it unplayable. In a platformer game, we can just make the gaps a little bit too big. In a puzzle game, we can just break it so there's no solution. It's really easy to make small changes and make a level really, really bad, and a level that would otherwise be great. So this kind of thing comes up a lot. So what do we do, right? So what kind of search algorithm could we use in an intensely spiky space like this? Take a couple minutes, think about it, go ahead and jump ahead if you like, and if you're watching this video later on. Okay, so what if we didn't just search one point at a time? What if we had a population of points spread evenly across the space and that we used to explore multiple locations at once? I told you multiple times early on that we can only know about spaces that we're at, right? We can only know about spaces that we're at and the neighbors of those spaces. But if we have lots of points, that gives us a better picture of what the space is like. We could in fact take, let's say, inspiration from an evolution. Maybe call it an evolutionary or genetic algorithm. Well, some clever folks did. Here's the intuition of what we're going to call genetic algorithms. They're also called evolutionary search or evolutionary algorithms. So what we're going to do is we're going to initialize a population of points. Now, typically, this is way more than 4 points, but for the purposes of this example, let's go ahead and just say it's 4 points. These 4 points. This is very similar for each one of these individual points to just initializing a random location for doing any other kind of search. The next step then, or the first step of the approach, the first step of the while loop, is to do a little bit of a random walk with some probability. So with some probability, we're going to have some of our positions change to one of their random neighbors. All right? Just like this here. We were at this gray X, now we're at this red X. Then from there, we're going to do this new thing called crossover. We're going to take good parents and mix them together to hopefully make good big jumps in this space. There should be another parentheses right there. Let's all pretend that there is one. So basically, right, if we took this point and this point, and we try to mix them together, well, if this is just a one-dimensional thing, then we can just get the midpoint. In that case, it'd be right here. Or this point and this point. And maybe, depending on how we do the crossover, we could either say this is the midpoint or this is the midpoint. Maybe we have one parent or another parent, and we can swap them either way. And then between these 2 points, we can say the midpoint would be maybe around here. Okay, so if we do that, then the next step is to go from all of our new points that we have, plus our original points, and reduce down to our original population size, back down to just 4, and just keep the best. So in this case, the ones with the highest fitness value. Then we're going to return to step 1 and just repeat. So again, mutate with some probability. Sometimes mutations will be bad. Sometimes this random walk will be bad, but sometimes it will be good. So we just do it at some probability. We're going to do crossover, so produce some children that are possible based on mixing together our current population points, and then reduce from there, and repeat over and over again until we manage to find the best possible thing, until our fitness isn't going up anymore. Then we can stop. So by doing this, by having a broader spread and allowing for bigger jumps, we can end up searching these big spiky spaces a lot better than other algorithms can. So let's go ahead and look at the genetic algorithm pseudocode. This is going to be very different from the greedy search or the simulated annealing. So what we're going to do is we're going to initialize a population of random points, very similar to the random points we were doing before. We can imagine them for a level or a piece of music or a story or whatever, of some specific population size. We're going to initialize time to 0. Genetic algorithms can run for basically as long as you let them. So we're going to set our time to 0. We can often think about every iteration of the while loop as a generation. So sometimes people will just instead call this a generation, and they'll have a generation cap. So they can only have so many generations. Then, while our average or our best fitness is below some threshold, so this is similar to when you looked for just having a particular points fitness below some threshold. But in this case, we have a population. So we can either look at the average of that population or the best possible value in that population. And while time is less than time. So while we haven't yet hit our max number of iterations, we're going to go ahead and increment time. Then we're going to mutate the population. This is when we do a little bit of random walk. Then we're going to add new members to the population through crossover, mixing together what we already have. We're going to reduce back down to that original population size based on only taking the best possible points. And then at the end, we're going to return our best member of our population, whatever our final population ends up looking like. So what mutated population does is, with some probability, often called the mutation rate, we're going to randomly swap out a member with a neighbor. This doesn't mean that when we hit mutation, we're going to mutate every single thing. Well, unless we have a mutation rate of like 1.0. But what this is going to let us do is get just a little bit of the benefits of a random walk, right? We can go to places we wouldn't otherwise get to. if we can sort of go through a valley, a place where you have to go downhill a little bit, but then you can start going uphill again. This is what a random walk can let you do. Now, crossover is entirely new. It's inspired a bit by biological reproduction, and the idea is that we want to take pairs from our population based on their fitness. This is similar to like evolutionary theory and its notion of fitness. The best things should pass on their genes, right? In this case, where their genes are whatever variables that we're searching over. So we're going to sample pairs from our population based on their fitness and mix their traits. There's lots of ways to do this mix. You could maybe take half of the features from one, half the features from another, average the features together. Lots and lots of ways to do it. Mostly, though, this is going to be a domain-dependent thing, so I'm not going to cover this. Then finally, by doing this mixing, this is going to allow us to intuitively make some big jumps that are hopefully good, since both of our parents should be good because we're sampling from our population based on fitness. Now, the reason why we don't just take our best things in our population and only let them have children is, first of all, that'd be awful. But second of all, how do you judge best? But second of all, we're not going to talk about eugenics. But second of all, what we want here, right, is to allow still some of that randomness, right? Because sometimes, even if a thing isn't for the best, by having it mixed with something that's good, we can do a big jump. So if we go all the way back here, we can, for example, see that if we mix, say, this position and this position, even if they weren't the best overall, that still would get us closer to this spike here, right? Say we had a position here. If I mix these two things together, just because they're better, technically, that doesn't actually get us anything better. But if I mix this and this, that gets us closer, right? So we want to probabilistically sample instead of just picking the best possible parents to always produce children. Then once we produce all these children, we need to reduce. So we're going to reduce our population back down to the initial size, and we only at this stage take the best possible population size members. Now, for some approaches, they're only going to take the children. This sort of enforces novelty and means that you can't just hold on to things from prior generations forever. But you don't have to do that. And notably, this step basically has all the benefits of greedy search. So this is where our sort of greedy search stuff comes in. Now, genetic algorithms are by far the most popular search-based PCG approach. There's a whole article in here where you can learn more about search-based PCG that talks a lot about it. There's 3 examples here. I talked about Darwin's Demons and Petals the other day. Galactic Arms Race is really similar, where what it's doing is it's looking at what weapons in the space game do players like to use, and let's make more weapons that are more like those things that the players like. Now that's interesting, right? Because that's very similar to how Petals is producing flowers more like what its players like, and Darwin's Demons is producing enemies that better fit the player. So in all of these games, and maybe the only time you want to use genetic algorithms is when you have a really complicated fitness function, like the player, that can't actually be represented computationally. And then maybe it makes sense to use a genetic algorithm, because it's going to do a better job of matching this fitness function, in this case, the player, than just trying to do constructive PCG or something like that and guessing, right, at what the player might like. But even then, we're going to have some pitfalls because you still have to measure what the player likes. So, for example, just because I use a weapon a lot doesn't mean I like to use it. Maybe I'm just using a weapon because I've fallen into a trap of its being the easiest thing to use, right? Maybe I'm producing flowers because it happened to be the flowers that I got initially. And it's not actually the ones I'd like the best if I could somehow tell the machine the exact kind of flowers I wanted. So with that, I'm going to end it for today. And on Monday, I'm going to go over a deep dive into the most popular PCG approach, which is constructive PCG. Talk to you then.